So the next section is about the optimum use of the variable input. Remember in our example, where's the table? In our example, this is an example. We're assuming capital is fixed, right? Capital is fixed. Okay. Now the question is, okay, how much labor to use to maximize a company's profit? But profit is measured by what? The dollar value, right? But if you look at this table, we don't have a dollar sign, right? So we need some additional information. This is purely from a technical point. Like if you increase one more labor, the additional output that you can produce. Right? But to maximize profit, we have to introduce the revenue side, the dollar. So the idea is very simple. So the optimal use of a variable input like labor. So we will take a look at it's called a marginal resource cost of labor. Now what is marginal resource cost of labor? If you use one more labor, what is the additional cost? Which is basically determined by the wage rate, right? Additional cost. And then the marginal revenue product labor. What's marginal revenue product labor? The additional revenue generated by each additional what? Use of labor. And for this one, we have basically three variables involved. So what are three variables? The first variable involved is the labor, yeah? Yes. Use labor, it makes contribution what? To the output. Right? And the output, well, if the price is equal to 0, then even you produce 100, the revenue is still equal to 0, right? Then this one has something to do with, with the revenue. So the marginal revenue product labor is, if you use one more unit of labor, what is the additional revenue? But we have to look at two things here. First is what? If you use additional one more unit of work, what's the additional output? The second question, if you produce additional output, what is the additional revenue? Marginal revenue. So the marginal revenue product basically is the marginal product labor times the marginal revenue. And the marginal resource cost of labor is the change in total cost if you use one more unit of labor. But in our example, this is extremely simple because we assume the wage rate is fixed. So basically this is what? If you use one more work, what's the additional cost? The additional salaries you have to pay. Right? So the optimal use, this is the equation. If you use one more unit of labor, the additional revenue should be equal to the additional cost. Rational people think at the margin. We always compare marginal revenue and the marginal cost. So here the question is how much labor to use. Well, you will use the number of works up to the point where the additional revenue produced by each worker is the same as the additional cost of each worker. That's the optimum. So in our example, remember we have the marginal product labor. In this example, we have the marginal product labor. And also, we're assuming the price is constant. So which make it extremely easy, the margin revenue is constant. So we can figure out the margin revenue product, which is the product of margin product, which is the product of margin product and margin revenue. And the marginal resource cost is equal to wage. We're assuming wage is constant. So now, if you look at this table, how much labor to use? And probably 3.5. Yeah? Why 3.5? Because this is when the marginal revenue product is the same as the marginal resource cost. And graphically, you will see here, this is the wage rate, and this is the marginal revenue product. It is when the marginal revenue product and the marginal resource cost intercept each other at this point. So that's the optimal solution. How much labor to use? How much labor to use? Okay. But now let's take a look at how about if we have two variables? In our previous example, we're trying to look at what? Only one variable. How much labor? What's the optimum number of workers you have to use? Then we have to answer the questions. Okay, if you use one more unit of labor, you need to take a look at what is the additional revenue, what is the additional cost, which is called a marginal revenue product and marginal cost, resource cost. When they equal, then that's the optimum number of workers. But here we're talking about what about if you can change in capital and labor at the same time? Yeah, changing capital and labor at the same time. So now we need to go back to the basic output. The basic output function. Capital and labor. Capital and labor. So the isoquant shows the combination of two inputs that can produce the same level of output. Remember we have this, you can change in the capital, you can change in the labor, and we have different outputs. Yeah, different outputs. But notice though, we have those what? Well. In other words, to produce goods and services, you have a choice. Yeah, either use a lot of capital and a small number of workers, or you can use a labor intensive. You can use a lot of workers and a very small amount of capital. So, for example, this one, you can use a 5 unit of capital and 1 unit of labor to produce 12. Or the other option is to use 6 workers and one machinery or one machinery. You get the same result. So this is called isoquant. But this is a different level though. This is what, 28 level. So if we move from left side to right side, what happens? The output level increases. But those curve, it shows what? Like this one, all 40, right? In other words, you can have different combination of capital and labor to produce 40 units of output. A lot of capital or a lot of labor, or in between, right? In between. So there's many choices. Okay. But in this case, though, we have it's called so if I make it clear, okay. So that's the isoquant. I have the labor here, and I have the capital here. But probably you will not use this portion. Now, what is this isoquant? Any combination of capital and labor will give us what? The level of output is 12. Okay. But you will not use this portion. If you produce, you will not. Why? This is almost like a, let's say this is a vertical. Okay, just make it easier. If it's just vertical, that means what? If you use this amount of labor, 1 unit of labor, and maybe 3.8 capital, you will produce 12, right? Or if you use 1 unit of labor and 5 units of capital, you can produce 12. So if that's the case, why even bother to use more capital? The resources are scarce, right? So for this part, you will not end up here. And same thing here, right? If we treat this as a horizontal. So in this case, so if you use this amount of labor, the same capital level, you can produce 12. So why bother use more labor? So it depends on the shape. If it's downward sloping, yes. Whenever it starts to show upward sloping, there's no trade-off. And then it's a no, right? It's a no. Because why bother? If you use the same capital for the less number of workers, you produce exactly the same output amount. So only the economical feasible range is this inside this loop. Because this is a positive slope. It's not a choice. Positive slope, not a choice. Only when there is a trade-off, then it's a choice. It's a choice. Is that clear? Either more capital, less labor, or less capital, more labor. But if you have to use both more capital and labor in this case, why bother? You would be better off producing heat. Is this clear? So mathematically, we have it's called a marginal rate of technical substitution, MRTS, marginal rate of technical substitution. And basically that's the slope of the isopod. The slope of the isopod. If we take a 10-unit point, that's the slope of the isopod. So the slope of the isopod is a negative number. That's why. So that's the changing in the vertical axis, changing in capital versus changing in labor. But add a negative number here, so this becomes a positive. Right? Also becomes a positive. So what is the marginal rate of substitution? Because if we move around this isopod from this point to this point, you start to what? Give up what? The amount of capital, but you start to use more and more labor. So for each additional decrease in capital, and in this case, you will start to using more and more labor, right? Labor. So the marginal rate of technical substitution tells us what? Tells us what?
It's about the relationship between those marginal productivities.
Mm-hmm. That's the changing in capital versus changing in labor. Right. So let's say how about if we're changing labor is always 1. Yes? Keep increasing the number of workers by 1 unit. Then this is what? The amount of capital you have to reduce. So you stay on the same isoquant. Isoquant means the same level of output. Right? It's a rate. It's a trade-off between the amount of capital and the number of workers you can use. So this is actually purely from the technological part, the ability for you to produce goods and services. It depends on technology. If there's technology to advance, those numbers will change. Or you can use a lot less workers if there's technology. A huge machinery, maybe all you need is 1 person. Right? It's possible. But this is only for a technical part. But on the other hand, we have to take into account what? Hold on. we have to take into account, how come, I think I lost some slides here. Did I lose some slides? Oh, we have also consider what? The cost, right? The cost of labor and capital. Because for a company, you only have this amount of budget, C is the budget, total amount of monthly spending. You have to spend out what? Labor and capital. And the W is what? The wages times the number of workers. That's what? Total labor cost. And this is what? The price of capital times the amount of capital used. So this is the spending on the capital. So this is the company's, it's called ISO cost line. Or this is basically the company's budget given the total cost. Then you can allocate into either using labor or capital. And the slope of this one is W divided, if we write in intercept and slope form, yeah, instead of the slope. So you find the slope is equal to negative what? W divided by R. W is what? Wage rate. R is the capital. So the optimal solution here and obviously in this case, so for this particular ISO cost line, and I think the total cost is $100. The total cost, budget, is $100. The price of labor is $10. The price of capital is also $10. So you can see in this case, if you spend all the money using the capital, you can have 10 units of capital, right? Because the total budget is $100. $100 divided by the price of capital $10, that's 10 units. If you use all the money to hire workers, then you can hire 10 workers. But how about if the price of labor changes? Say, instead of $10, now it's only $5. Now what happens? $5, you have $100. If you spend all the money on using the workers, you can hire what? Now you can hire 20 workers. Okay, a different line. What happens if the company's budget increases from $100 to $200? It shifts up, right? Shifts up. So if we take a look at here, we have two things here. One is what? The ISO quant. The ISO quant basically shows us what? The company's production capability. The trade-off between trade-off between capital and labor. The amount of capital labor used in the production. Okay. And on the other hand, nothing's free, right? Nothing's free. So we have to take into account the cost of capital, cost of labor, the total budget allowed. So now, given this budget, so what is given this amount of budget? What is the highest level of the output the company can produce? Right? Or, in other words, given this output level, what's the minimum cost for the company to produce this this level of output? And the optimal solution is what? The optimal solution. How about this point? It's good, right? Because you have more output, 228, not 12. But given today's budget, this month's budget, you cannot reach it. You cannot reach it. Okay. So the optimal solution basically is the tangent point between the ISO cost line and the ISO quant. So you'll find basically the optimal solution is This is the condition. This is the condition you have to understand. It's very similar to what? How does a consumer satisfy? In this case, you'll find the optimal condition is the marginal product labor is equal divided by the wage rate is equal to the marginal product of what? Capital divided by the price of capital. So what does this mean? This means the marginal product of the last dollar spent on labor is same as what? The marginal product of capital is spent on capital. The last dollar is spent on capital. The marginal product is the same. Okay. So if you look, so this left side is equal to right side, and then this is what? The optimum combination of inputs to minimize the cost for a given output level, or maximum the output for a given cost level. Given cost level, this is the highest output level you can achieve. Or given the output level, this is the minimum cost to achieve to reach that output level. So it shouldn't be left side equal to right side. But if left side is not equal to right side, so this will not be an optimum. So for example, if left side is equal to 5, marginal product labor is 5, marginal product labor is 4. Both of the wage and the labor is $1 each. Yeah? So the left side is 5 divided by 1, right side is 4 divided by 1. Okay, now what do you need to do to restore the equilibrium? Do you have to have more labor or more capital?
More capital.
You have to have more capital or more labor?
Says something.
The left side is equal to right side. So we have to make the left side smaller. How to make the left side smaller? Remember the diminishing marginal product labor? Now what is diminishing marginal product labor? The more labor you use, what happens to MPL? If you use more and more labor, what happens to the marginal product labor? It decreases. So in this case, you should use more workers. You know why? If you use more workers, what happens to MPL? Will start to diminish. Now it's 5. If you use more and more workers, it can become a negative number. Remember when the fighting was chosen? It's getting smaller and smaller. So in this case, you should use more labor. Right? You use more labor to reduce the marginal product. So probably this will be a quiz. In the quiz you will find it. So basically, okay, you first decide which side is larger. If this side is larger, make it smaller. How to make it smaller? Use more resources. Use more workers. Because if you use more workers, according to the law of diminishing marginal product, the marginal product will start to decline. And this is an example of what? How about you have more and more budget? More and more budget. So in this case, this is probably not in the short run. How do we know this is not in the short run? What's the definition of short run? In the short run, some costs are fixed. But here, we have two inputs. Both inputs are variable. You can change in the left. You can use more and more capital. So this is it's called expansion pass. But expansion pass is more like in the long run. You can vary. You can change in both the level of labor and the capital. And then the last condition is how to maximize profit. A company produces two products. Yeah, uses two resources, labor and capital. So if that's the case, to maximize the profit, again, we use the marginal rule. Yeah? The marginal resource revenue product of labor is equal to the wage rate. And the marginal resource revenue product of capital is equal to the cost of capital. The cost of capital. So that's the optimal condition. And the last part has something to do with return to scale. Return to scale is, again, it's a long run decision. So we have a production function. So the output level is determined by the number of workers and the amount of physical capital. Now the question is, what happens if I double the number of imports? What happens to the output? So in this case, let's say if I increase the labor by H factor, capital by H factor, so what happens to the output level? If the output level is also doubles, for example, H is 2, yeah? So if lambda is equal to 2, that means what? Doubling the imports doubles the output. Then this is called constant returns to scale. But how about if lambda is equal to 3? So that means we're doubling the quantity of imports, and we're more than double the quantity of output, right? So that's called increasing return to scale. And if lambda is less than h, so if h is equal to, lambda is equal to 1.5, then this is called decreasing return to scale. Doubling the total imports will result in less doubling the quantity of output. So that's the returns to scale. But return to scale is what? You increase both labor and capital at the same time. And this is the graph shows. So in this case, what happened to the quantity of labor capital? You double it, right? Double it. How about output level? You double it. So that's a constant return to scale. How about this one? More than double, right? More than double. Because double is 200, right? This is 300. And how about this one? Decreasing returns, right? Because you double the quantity of import, but how about output? Lessen, right? Lessen the quantity of output. So constant increasing and decreasing returns to scale. And I have some data here. Yeah. Depends on the industry. Depends on the industry. But actually, most of them are very close to 1, right? Most of them are very close to 1. And for industry, some industry is less than 1. That means if it's equal to, so for in the same return scale, you can see most of the actually the data is very close to 1. And there is a special production function. It's called Cobb-Douglas production function. Well, it's still basically the quantity of output is determined by what? Capital and labor. But in this case, we have a specific functional form, so to the power of A and to the power of B. And A is a coefficient. A is a coefficient. But, so this is a nonlinear, right? If you had a pre-calculus, you know this is a nonlinear function. Okay. And then how do we convert this into a linear function? You take a log from both sides. You take a log from both sides. Natural log from both sides. If you take a natural log from both sides, and then you convert this nonlinear function to a linear function. A linear function. And actually, if we want, we can use the regression model to estimate what we have the dependent variable, depends on what? K and L. We can estimate the coefficients. So actually we can estimate the Cobb-Douglas functional form. And for the Cobb-Douglas function, the A, which is on the power of what? K, right? Power of K. B is the power of labor. A actually is the output elasticity of capital, and B is the output elasticity of labor. And mathematically, actually, we can prove it, but I'm not going to touch this subject. And A plus B will determine what? Constant return to scales, and increasing return to scales, and decreasing return to scale. So if A plus B is equal to 1, constant return to scale. If it's greater than 1, then it's we'll have an increasing return to scale. If less than 1, then we'll have decreasing return to scales. And in real life, in real world, basically, the company will have convert the Cobb-Douglas functional form into a linear functional form. Then use regression methods to estimate those coefficients, especially A and B. Good. So the A is basically the output elasticity of labor. Remember what is output elasticity of labor? That's changing in capital versus changing in labor. And B is the output elasticity of capital. Okay. So I think the homework assignment for this week are easy. So hopefully you can figure it out. We'll see. The homework is due next Monday, midnight. So in case you have questions, we still can discuss in class, right? In class, yes. So that's the beauty of having the due date on Monday night at 12. Yes. And the midterm exam are also due next Monday, 12. But the midterm exam, the question is similar to what? The homework, right? Yes? Okay. So make sure you, the due date for the project is the last day of class, which is, I believe, December something. But the midterm exam is due next Monday, and also the homework is due next Monday.